Hi everyone, my name is Vladimir, and this session will be about the fundamentals of blockchain technology to give people a better understanding of what it is, how it works, and most importantly, where it can be used. Now, I know there has been a lot of buzz and hype around blockchain and distributed ledgers. Some of you might have come across some of these words and know their definitions. Some might have only heard of these words, and most are probably grinning at the funny words like sharding. Now, there are many levels of knowledge around this technology, and people get stuck around different levels of the learning curve. When you begin, you're absolutely clueless. You're not sure where to look, what to look up, and what to search. As you progress, you become naively confident and then discouragingly realistic. I believe I have just left the discouragingly realistic stage, so this goes to show that there are a lot of people on this journey of discovering blockchain and distributed ledgers. Keep learning, keep searching out every different new term that you pick up. Google it, find out what it means, find out how it works, and soon we will all be at the mastery level. So today, I'll be covering the trends that we see around blockchain. I'm going to describe what it is, how it works, and then I'm going to go through a Bitcoin transaction example to try to solidify some of the simple aspects of how blockchain works. And then we're going to get into smart contracts and some of the use cases. So if we can take a look at the graph to the left, there's been very little activity from 2011-2013 in regards to the published patents that are related to blockchain technology. Now, this chart is not necessarily complete because a patent application will typically publish 18 months after the patent has been filed with the USPTO, unless there's a request not to publish the pending patent application. So there's still patent applications that have been filed with the USPTO that have not yet been published. And in another year, the numbers for 2015, 2016 should be much higher. But clearly looking at this chart, the numbers are trending upwards. And most of these patents are related to Class 705, which is directly related to financial matters. And this is perfectly in line with some of the expectations that we should be seeing that surround the early adaptations of blockchain technologies. Now, this is good news because more filings indicate more investment, more planning, and more established businesses are entering this technology space. There are very highly known names where the patent names are appearing. Amazon, Apple, Bank of America, Facebook, Dell, Goldman Sachs, IBM, MasterCard, Visa, Wells Fargo, and there's many more. So another trend to look at is the Gartner Hype Cycle. This gets published yearly, and this is around the emerging technologies. So in 2015, we don't even see blockchain on their list. 2016, blockchain appears at the top, and it has an expectations of roughly 5 to 10 years to make mainstream adoption. So what is the blockchain? A blockchain is a type of distributed ledger. It's comprised of unchangeable and digitally recorded data in packages called blocks. Each block is then chained to the next block, and these allow blockchains to be used like a ledger, which can be shared and accessed by anyone with the appropriate permissions. A file of this file is maintained on every node in the peer-to-peer network. This, with some basic math security, is all there really is. It's a group of computers maintaining a ledger. Unlike a bank, a group-maintained ledger rather than a central authority introduces a number of important differences. And unlike a bank, where you only know about your own transaction, everyone knows about everyone else's transactions. So let's start from the very beginning. What is a ledger? It's a balance of debits and credits. Who is it going to, and where is it coming from? Now, what kind of network types do we have? Well, we have centralized, where one server node and then all the client nodes around it. And it's clear taking out the center node, and the network breaks down. Any example of this could include a structure where there's a central authority and then everyone reports to it. And it's becoming increasingly difficult to protect such centralized databases. It's a major security concern and a major scaling concern. The next one that we have is decentralized. The internet of today is an example of a decentralized network. The client nodes are the individual computers in homes. They only have one connection to the outside world via their ISP. The server nodes can be thought of the ISPs themselves. Most of the time, they have multiple connections to other ISPs and networks, and etc. Now, a decentralized network is more desirable than a centralized one due to its fault tolerance and difficulty of being shut down. And lastly, we have distributed. And in a distributed network, a node has as many connections as possible to other nodes. Therefore, disrupting communication amounts to almost destroying every node or every link. Every node is capable of forwarding communication from other nodes. It acts as a server for others and, of course, as a client for itself. Distributed networks are the most desirable ones from a reliability perspective. There are four main properties of distributed ledger technology. 1, there's reconciliation through cryptography. 2, the availability of many copies provides transparency to the network. 3, ownership of funds is verified through links to previous transactions. And 4, irreversibility. This prevents tampering with previous transactions. Now I'd like to do a demo, which is built by Anders Brownworth, who teaches blockchain technology at MIT and did an excellent job in creating this demo. So I'll show you how he has explained it, because I found this to be the best resource on the internet of really figuring out how and why this works. So in this interactive demo, we're going to start off with the hash. The SHA-256 is the most popular one available, and essentially it's a cryptographic method where you put something in and you get a hash, which is a fixed length alphanumeric output back. The mathematics behind this cryptography makes reversing the hash impossible. So with this blank data in here right now, the hash is the one that you see here. If I put anything in, even if it's just a space, you can see that the hash changes. I put another space in, it changes again. Anything I write in here, every character is going to change the hash. As you can see, anything I write is changing the hash. The full output, the 32 bytes, are changing. So this 32 byte output is going to be what's going to be added into the block. Now let's extend that idea to the block. Okay, so we start off block number 1, a nonce, which I'll explain later, and data, the blank data that we just saw. But now the hash starts with 4 zeros. This is relatively unusual, but we're going to call this block digitally signed because it starts with 4 zeros. So if I change any piece of the information that's inside, you can guess that the hash is going to change. Okay? So if I type the same thing, hello world, the hash has changed. And now it does not start with 4 zeros anymore, and the block is not digitally signed. So what we do is we need to find a nonce that will fit the data inputted, that will output a hash that starts with 4 zeros and makes the block digitally signed again. So if I click this button here, mine, you've been looking at and wondering what it does. When I click it, it's going to run from 0 upwards, and it's going to try to find a nonce that will equate to a number where the nonce plus the data is going to output a hash with 4 zeros. So it's going to try every single number going upwards using computing power to find that number and tell us what it is. Oh, that one was relatively quickly. So it's found 18,000. So from 0 upwards, found 18,014. That nonce plus this data has given us a hash that starts with 4 zeros, and now the block has gone green again because it is now digitally signed. If I change it again, the hash again changes. It doesn't start with 4 zeros. It again has gone red. If I remine it, it's going to do the same process, go from 0 upwards. Now it's found 124,000, and the hash again starts with 4 zeros. Now this data input could be anything. It could be one word, it could be a sentence, it could be the whole Library of Congress. I could put images in here, videos. It doesn't matter how large it is. The output of the hash is going to be 32 bytes, and it's going to change with every single little difference that I make with the data being inputted in here. So high is going to have a hash, and then high space is going to have a totally different hash. And again, going back to the principle, if I mine it through, I'm looking for a nonce. It's found one now, a little bit longer, 44,000, but now the block has been digitally signed. So let's extend this idea to the blockchain. Okay, here I see block 1, 2, 3, 4, and 5. I have 5 different blocks, but now what they're doing is that they're referencing each other. And this is the link that I was talking about before. The previous hash here is pointing to the hash that's outputted at the end here. Then this has a previous, and it keeps going back. The same data as we just saw added the previous hash. So in addition to what we just saw, we have, we have the previous hash. As you can see, this is the first block, block number 1, and this is called a genesis block. And it just has a dummy hash, which is all zeros, which is fine. But to this example, if I go to block number 4, and we see that this hash is AE8BBC, this one has the previous as AE8BBC, but this hash now ends with 74DD. So if I go in here, because this hash that's currently linked to this block has no data in it, if I type anything in here, I clearly change the hash, but now this hash has changed and the previous hash in this block has changed, which means this one's not validated and this one's not valid either. Now what I need to do to alter this chain is I need to mine this block, block number 4, and then I need to block the second one. I need to mine, block number 5. So let's do that. With spam and eggs being in here, now the only input. Now I've got a new hash that starts with 4 zeros. The previous one takes it. However, with this previous one, this nonce in the blank data, this one's still not 4 zeros. But I can remine it. It's going to find me a nonce that with this data, with this previous hash, it found a new nonce that we just saw that has now equated this hash to start with 4 zeros. It is now, again, valid. It is digitally signed, and it is good to go. Now, how do I know the blockchain has been remined? If I go back here, change something, mine this, mine that, it's all green. Well, how do I know? Well, this is where the distributed aspect of blockchain comes in. So this looks the exact same, okay? But now I have several peers. I have peer A, peer B, and peer C. And this shows the exact same hash. If I go to the end of this one, to the end of this one, and to the end of this one, we can see that the ending hash, this one's a bit longer, I think it's just the size of my screen, but 17C, 17C, and 17C. So they all have the exact same chain of blocks that each peer has. It's what we talked about before, where every single transaction file is distributed to every peer. So that's what we're seeing here. So if I change one peer, if I go to peer A and I input something into this data, I want to change something within this specific transaction block. Okay, so this has changed. It has invalidated this block and it has invalidated this block. So now I can remind this, just like we did previously. It's gotten the hash that makes it valid. I can do the same thing with this now. Remind this one. This hash now ends with 9A, but these ones still end with 17C. Okay, so essentially what we have is 17C, 17C. These two peers are telling me that the chain should be ending with 17C. And it should be going back and going back and going back, but essentially it's 2 against 1 right now. And consensus is going to say that this one is wrong. This one is still the difference. Democracy dictates that it's 2 against 1. They are correct. And this is the best part of having a copy on many computers, because we can easily and quickly see if all blocks are identical. And if they're not, we're able to identify which ones are the non-correct ones. And this simple principle is the entire blockchain. There's not much more to it. What we can then do is add a couple more aspects to it, but the general principle is what we just described here, is that each node has a copy of the transactions, and then we can validate, okay, which ones are the correct ones. Tokens. And this aspect is able to show us where money is flowing from one to the other. Here, this becomes very important, because if I go to the end of these ones, I could try to change the fact that one person sent more money than they did to the other person. And this is where immutability is very important, because resisting any kind of modifications that for things that have happened in the past becomes very valuable to the network. So if I try to change that instead of $14.12, $30 went from Denise to Edmund, well, that's invalid. That did not happen. It's going to tell me that that's wrong. But if I go back to 14.12, well, that is a correct amount, because that all of this information, which is what we saw before, I can put anything in here in this data block, is going to tell me a specific hash that, included with the other hash, has outputted a digitally signed version. If I change this to 30, well, no, that previous hash plus this data plus this nonce is telling me that this hash is incorrect. It's not digitally signed. That's not the right information that was given at the time. Go back. It's digitally signed. This is very important because we're able to remember money movements. Okay, but we're not listing a balance. We're not saying that Denise has $14.12 in her bank account. Denise might have more than that, and what we can do is we can go backwards to figure out how much she has. But to do that, we need to establish a Coinbase. In a Coinbase, essentially from the beginning, when any cryptocurrency starts, there is an initial transaction that essentially invents $100 out of nowhere, gives it to Anders, okay? If we trace money backwards, if we go to block number 4, or we go to block number 3, and we say, okay, $10 went from Emily to Jackson. But do we know that Emily has $10? Well, we don't have her balance, but we can go back to previous transactions and see if she's received $10 from anybody. Okay, Anders actually sent her $15 from the original 100 that was created. He sent 15 to Emily. So now we know Emily does have $10 to send to Jackson. So therefore, we are able to validate this transaction because she actually does have that coin, that money, that value in this specific currency, in this specific cryptocurrency, and she's able to send it to Jackson. So what we're doing here now, we're using the hashes, we're using the blocks, we're using now transactions. We're also now included a Coinbase where we've given, essentially this is monetary policy, where we created money into the system and now people are able to use it. And as you know, with any other currency currently out, if it's not backed by gold or any other commodity, it's only given value because people think it has value. Similar to the US dollar, we use it because we think it has value. We know that when we go to a shop, people will accept it and give us things for it. It goes for the same thing for cryptocurrencies. And we can see the same thing now with the Coinbase, that if Jackson is sending Alexander money and somebody wants to go in here and change that, instead of $2, Jackson sent him 40, the block is invalidated. We're unable to use this. This is the incorrect chain. And now everybody has access to this, and they're able to see and they're able to validate for themselves. Every single person on the node that joins the network is able to validate themselves if the transactions follow suit. If this person actually has money, they can trace it all the way back, all the way back, all the way back to the very first block. And now obviously there are computers that do this for us, that every time it will validate the network for you to make sure everything's okay. We're given autonomy and self-sovereignty over our money. This creates a trustless proof mechanism. And this is the most important part. This creates a trustless proof mechanism. So instead of transferring the asset, what can happen is a worthless copy can be transferred while the original asset is maintained in the own account. And the traditional way to mitigate this risk is to use trusted third parties like a bank to act as a centralized authority, or to use cash. Blockchain technology is going to enable us to shift this trusted third party role to the whole network instead of a centralized party. And this file is maintained in every node in the peer-to-peer network, as I just mentioned, and everybody is able to validate their own transactions, validate every transaction for themselves, and make sure that everything is okay and working correctly. Now, I'm glossing over the main points, but this is how the blockchain works, and this is why it is very important, very useful, and can be applied in many different aspects. So the one cryptocurrency that we all know, that we all should have heard of, is Bitcoin. It was created in 2008 by Satoshi Nakamoto, and it's not backed by any currency or commodity like some of the fiat currencies. And it's only backed, like I previously mentioned, on the belief that this digital money is worth something. And this is very similar to the US dollar. So to get a better understanding of Bitcoin and the underlying technology of blockchain that powers it, I'm going to run through a simple example to show you how it works. Now, this infographic is provided by wistechie.com. So here we have Bob and Alice. Okay, Bob is an online merchant and Alice is the buyer. They both have Bitcoins in their wallets. So let's say Alice wants to pay with her Bitcoin that she has in her wallet. They're stored, and she wants to send it to Bob for a purchase that she's going to make. Okay? And Bitcoin has addresses. It's a string of letters and numbers. It's an alphanumeric string that looks similar to this. Okay? Each address then has its own balance of Bitcoins. But remember, when we discussed balances, the wallet is able to run through all of the transactions on the chain and present to you in a front-end UI environment what your balance is. The blockchain itself doesn't hold a balance. Just keep that in mind. So then what we do for this transaction is we create a new address. Okay? Bob, who's a merchant, is going to create an address where Alice can send her Bitcoins to. So he does the creation. He gets an alphanumeric string similar to this. Alice goes in her wallet, inputs this string, and says, I would like to send $20, whatever the payment may be. Then what we have is the private and public key cryptography. And this is called the cryptographic key pair. Public and private key cryptography ensures that transactions are authorized. Okay? You can think of the private key as being the true password, and the signature as being an intermediary that proves you have the password without requiring you to reveal it. Because people that are validating these transactions, miners, you don't have to show them your private key, because then if you did, they'd be able to use it and probably steal Bitcoin from you. Without you doing that, the signature acts as an intermediary. The signature acts as you proving that you have the password without you requiring to reveal it. So through the math, we're able to verify that the sender owned the private key without actually seeing the private key, which is very important, which is why it goes back to that trustless mechanism. We're able to trust everybody with value transfer on the internet now. And that is very important. That is why blockchain and Bitcoins are very important. Now, because the signature depends on the message that you're sending, whether it's how much money is going through the transaction in this particular example, or whether it's smart contracts, it's going to be different for every transaction and can't be reused by somebody for a different transaction. So nobody can modify that message while passing it along through the network. And to keep anonymity, you can create a new public key for every transaction. On top of this, you're able to use Tor networks to hide IPs. Be able to use VPNs. This is why Bitcoin first got such a bad report, because it was used on sites like Silk Road to conduct illicit activity, to conduct purchases that weren't allowed by law in the jurisdictions that these purchases were going on in. And if you're interested in learning more about digital signature math, you can check out ECDSA on Google, the elliptic curve digital signature algorithm, mathematical trapdoor, and many more. And I suggest you check these things out just to understand what's behind the curtains, what kind of mathematics is driving this, because the cryptography is very top-notch, it's very secure. For you to understand how safe the network is, you got to know what's going on. I don't have time to get into it right now. I'm going to continue on with the transaction. So then, once the private key and the public key transactions have happened, the account owner has verified that she sent the money, and Bob verifies that he is receiving the money. Then the miners, Gary and Garth and Glenn, I guess, in this example, are going to go through that process that we went through in our interactive blockchain example, where they take the data, which is now transactional amounts being shared, and they're going to try to find a hash, which is going to make it digitally signed. So they take, these transactions, and in the Bitcoin protocol, those transactions over 10 minutes get grouped together and get put into a transaction block. So all the transactions that occur within 10 minutes get put in a block, and then the miners, which is just a set of computers, are going to calculate for these cryptographic hashes, which uses a lot of computing power. And what they're going to do is going through the same example that we went through. They're going to try and find the nonces that makes each transaction digitally signed. So it's the same thing here. It's the hash value, the transactional block now with many transactions, the nonce, and the new hash value. And then this block is linked through new hash value of the old one. And it keeps going and it keeps going, which we just saw. Now at the end of this, the miners, who have expended great computing power to figure out which hash is the correct one, then share it to the network, and they legitimize that this is the right transaction block. These are the right set of transactions that occur within that minute. They push it up to the network. The network accepts because it is a lot easier to verify. It's a lot easier to check than it is to actually compute and figure out which one is the correct one. So as soon as the first one gets it correct, sends it up to the network, everyone verifies, yes, this is the correct set of nonces and hashes that validate these transactions. Every node then in a network accepts it, and it gets added to the blockchain. Now when it gets added to the blockchain, that money is now sent. That money is now settled and sent from Alice to Bob. That was all of the processes that went on in the middle to make that happen. So let's talk about mining for a second, because where do bitcoins come from? Well, with paper money, governments decide when to print and distribute, right? But here there's no central government. We need to solve math problems, and the first one to get it right gets issued a certain amount of Bitcoin in exchange. That's where that Coinbase originates from. And this creates incentives for more people to mine. Miners approve the transactions. Now, there's a lot of miners currently on the Bitcoin network specifically, and it becomes very hard for individuals to solve these problems. There's now pools of miners that find solutions faster, and then each miner rewarded a proportion. The mining aspect is called proof of work, and by requiring difficult mathematical equations to be solved, so-called would-be hackers are pitted against the entire network in a race to solve the problem. They are unlikely to win. Now, proof of work protocols are often amounted to puzzles that can be challenging to solve and require serious computation effort. Now, this effort can be easily verified, far less than to conduct the effort in the first place. Now, Bitcoin uses proof of work, or POW, when creating transactional blockchain. And these have been proposed in the past, for example, to deter spam email. It can be tied to a particular message. Instead of paying for a stamp, you pay for CPU cycles. So legit senders sending small amounts of emails causes a minor deterrent for them, but it's a great impediment for somebody spending tons and tons and tons of email, 100,000 or more. It becomes prohibitively expensive to expand so many CPU cycles, and therefore it impedes spam. So one thing that we didn't mention is the Merkle Tree, where each block contains multiple transactions, and then each transaction's data is passed through a hash function, now containing 4 unique hashes, one for each transactional block. Then these pairs of hashes are then combined and passed through another hash function. This produces 2 separate and unique hash functions, and based on the combination of these previous hashes. So when combined again, it forms the root of the hash, which is called the hash of hashes, and this forms a complete Merkle tree. Merkle trees allow for the detection of mutations to any transactions in the block by rerunning through the process on each transaction and comparing to the original root hash. Whereas Bitcoin is an unpermissioned public distribution method, there are alternatives that only allow certain groups to enter the blockchain data, and these are called private ledgers. So if we think of it in this way, how many copies of the ledger? 1. Okay, well that's the traditional ledger. That is the personal bank account where you're able to see your own transactions. If there are many copies of the ledger, then we need to ask who can use those copies. If only one owner group is able to use those copies, then it's a permissioned, private, shared ledger. If anyone can use those copies, then we need to make sure who is able to maintain the integrity of the ledger. If only trusted users are maintaining the ledger, then it's a permissioned, public, shared ledger. And if anyone's able to maintain the integrity, then it's an unpermissioned, public, shared ledger, just like the Bitcoin example we just went through. So the current thinking is that the most likely application for the financial sector will be a permissioned blockchain. Now, we think of consortiums within banking, insurance, and asset management that will maintain the ledger and in cooperation with regulators allow members to participate. And the current one that's listed here is the R3 consortium. Currently, they have 80 banks, financial institutions, insurance companies, regulators that are cooperating within that. You can check them out more. And then another one for the permissioned public shared ledger is Ripple, which is also making waves in the industry. And I highly suggest for you to check them out. So now we get into the most interesting part, or at least the most interesting part for me, and that is smart contracts. Smart contracts are programs that run on a blockchain and reduce the risks and costs of interacting with other people. So as we saw with Bitcoin, it allowed us to create a trustless mechanism of interacting and exchanging value with people that we have no idea who they are, no idea what their identity is, only know their Bitcoin address. So smart contracts, they store rules for negotiating the terms of a contract, and they automatically verify the contract and then execute the agreed terms. So today's systems operate in a central model. Parties who wish to interact with each other do so through a central system. There is trust that is laced on the central system by all parties. Okay? Untrusted parties can transact directly with each other by using smart contracts and by being self-executing and having property ownership information embedded. They can solve the problems of counterparty trust. They can execute agreed stored processes when triggered by an authorized or agreed event, just like traditional systems. And all contract transactions are stored in chronological order on the blockchain for future access, along with a complete audit trail events. Now, if any party tries to change it, it's detectable and can be prevented. It goes back to the immutability of the blockchain. If any party fails, crashes, bankrupts, or the system is going to continue to function without any loss of data or integrity. A strong benefit of code-based transactions is the transactional efficiency of being able to automatically generate contracts. And what's probably more beneficial than the efficiencies gained by automation is that the fact that the progress in artificial intelligence research will soon allow machines to understand more and more complex logic, which will ultimately lead to a system being capable of alerting a drafter to inconsistencies that often go unnoticed by human drafters. The ability to have a machine apply this sort of compliance logic would save certain industries a massive amount of time and money, especially within the financial and security sectors. There are many applications where the blockchain has the potential to disrupt massive industries, whether it's securities, record keeping, digital currencies, smart contracts. There are a lot of cool companies doing a lot of great things in the space, and I'll show you a slide on it a bit after. But for example, there are investment banking products on a blockchain. Recently, a group that included Bank of America, Merrill Lynch, Citi, Credit Suisse Market, and DTC completed the first trial of a credit default swap that was fully traded via the blockchain. This credit default swap got its own wallet address, and a smart contract written on top dictated the terms for payment. A different company that is concentrating on investment banking applications and post-trade financial services is Digital Asset Holdings, which is run by Blythe Masters, who was a former executive of JP Morgan Chase. It is clear that the inefficiency gains on the investment banking operations are very large. New products that were previously not profitable due to the large amount of administration costs relative to the revenue potential are currently becoming available. So here's a use case that we're able to apply the blockchain to and get direct efficiencies. Know Your Customer, KYC, is a process that requires banks to validate and verify primary documents as part of due diligence. Regulations are such that the task of due diligence and investigation is still handled by the client onboarding teams at financial institutions, given the business and the reputational risks involved. Every bank and financial institution has to perform KYC process individually and upload the information and documents to their central registry. Banks can then access the stored data to perform due diligence whenever customers request for a new service within the same banking relationships. Right? So the KYC process can delay business as it can take 30 to 50 days to complete a satisfactory level. Right now, there's more than 1.3 million bilateral correspondent relationships across the industry. That's a huge administration burden each time a relationship is added or information needs to be updated, and this becomes a hugely incredible expense. 2014, it was estimated that global spending on AML compliance amounted to around $10 billion. Utilizing the blockchain creates the potential to create a shared golden source of data and can reduce errors and the need for reconciliation. A blockchain-based registry could potentially remove the duplication of effort in carrying out KYC checks. The ledger could also enable encrypted updates to client details to be distributed to all banks in near real time. This KYC ledger could also provide a historical record of all documents shared and compliance activities undertaken for each client. This will form the evidence needed to provide to the regulators. Now, to work, there are several things that need to be met. First, the counterparties making the updates to the ledger must all be trusted parties, such as company registries, law enforcement bureaus, etc. Second, there must be already an international legal entity identifier to ensure that all trusted parties are updating the right record. I mean, you can imagine what kind of nightmare it would be if multiple records exist for one company and everybody's updating different records. Finally, we need to be using some kind of permissioned public blockchain where a set of parties can update and the rest can read off the blockchain. Then there could be a possible solution to using the blockchain for KYC. So another aspect that's related to KYC is digital identity and digital signatures. Once a corporate has had their documentation verified once, a digital identity could be created for that customer. This is essentially their digital passport for transacting in financial services and would be appended to every transaction they undertake, effectively signing their transactions for them. Now, this potential model of using a holistic digital identity provides significant benefits over the simple usage of blockchain for KYC. And namely, it has enhanced customer experience through only having to submit documentation once, increased security, and less opportunity for identity theft. The banks don't have to go through KYC checks for every single customer. If they've already been checked and given a digital identity, they just use that digital identity. This provides increased security through near real-time distribution of updated documentation, verified digital identities, and the opportunities to share in near real-time fraudulent transaction details. It provides increased transparency and the ability to get a full transparent audit trail of all transactions. Here's a list provided by William of some great companies doing work in this space. So there's some current companies working on this KYC and AML use case. IO Digital, ShowCard, Unique ID, OneName, Ascribe, TrustAtom, and Civic all offer businesses, including banks, the ability to scan customer documents, identify information, and then generate private and public keys to seal them before the data is encrypted and then sent to the blockchain. The fintech startups Chain Analysis and IdentifyMind Global help banks comply with KYC and AML regulations. Here are some companies that are in the space of specific use cases, whether it's peer-to-peer payments and lending, custodian services, smart contracts, government services, gambling, predictive analytics, and decentralized markets like OpenBazaar. I suggest you check these companies out, see what they're doing, how are they operating, how are they interacting with the blockchain, how are they interacting in the front end with the consumers. There are a lot of great ideas coming out right now, and there's a lot of progress to be made. So, in closing thoughts, blockchain is hyped, but it is here to stay. The technology is currently being hyped up, as we all know, as witnessed by large investment flows from private investors. Technology is here to stay in the long run. It is in its infancy stage, and there are several challenges to overcome before mass adoption is possible, and regulatory and technical issues are the most decisive. It is evolutionary and not revolutionary. It is going to be a powerful combination to include blockchain and smart contracts. The rollout will be evolutionary rather than disruptive. It will allow incumbents to react to the new technology and find ways to incorporate it into their current IT systems. And there are going to be winners and losers. I mean, it's clearly too early, I believe, to identify clear winners. Losers are going to drop off. Winners that have a solid technological platform that will adapt to the needs of the consumer are the ones that are going to survive. So thank you for your time. I hope that if you're still around and got to the end, you learned something new. You at least found out how the blockchain works. If you would like to connect, message me on LinkedIn, or subscribe to my YouTube channel and send me a message here. I'll be happy to respond. Thank you.